Welcome to this online presentation for SIGCOMM 2020 paper, Leveraging Ambient LTE Traffic for Ubiquitous Passive Communication. My name is Zichen Chi. I just got my PhD from University of Maryland, Baltimore County, and will join Cleveland State University as an assistant professor very soon. This is a joint work with my colleagues Xin Liu, Wei Wang, Yao Yao, and my PhD advisor, Ting Zhu. In this presentation, we will first introduce the motivation of why we developed an LTE-based backscatter system. Then we will talk about the 3 technical contributions we made in this project. Finally, we will answer a few frequently asked questions raised by the reviewers and our readers. Let's move to the motivation first. Backscatter, especially ambient signal-based backscatter, is a promising future for Internet of Things devices. Recently, researchers proposed systems to utilize different existing signals like Wi-Fi, Bluetooth, Zigbee, and LoRa for backscatter communication. For example, the first system used a Wi-Fi signal to carry backscatter data published in SIGCOMM 2014. From Hitchhike in Census 16 to Backscatter in Mobius 18, the Wi-Fi signal-based backscatter systems were improved to support newer Wi-Fi protocols like OFDM and MIMO signals, respectively. Interscatter and FreeRider were proposed to use Bluetooth signal, and FreeRider can support Zigbee signal as well. Later on, several systems were developed to use the newer IoT protocol LoRa. However, we argue that these signals are not excellent carriers for backscattering because of the limited coverage in space and time domains. So in space domain, for example, LTE has much wider coverage across the country or even the world. By looking at these figures, it compares the coverage between LTE and the LoRa. We can see that our LTE has much wider coverage. So in time domain, the traditional backscattering techniques could fail due to intermittent traffic patterns and shared channels. On the contrary, the continuous LTE signal allows reliable backscatter communication. Thus, we proposed an ambient LTE-based backscatter system, airscatter. This system utilizes ubiquitous LTE coverage and the continuous LTE excitation signal for low-power passive wireless communication. Now that we have discussed why we designed an LTE-based system, we will present the technical contributions of this work. The first contribution of this work is that we looked at a new aspect of backscattering. That is the ubiquitous coverage. We discovered that LTE traffic keeps high occupancy rate over time and space, which makes the LTE signal an excellent candidate for backscattering. The second contribution is that we solved many challenges, including the synchronization problem. In this challenge, we want to avoid modulating on some important signals like the PSS or SSS signal. And we solved the modulation efficiency problem especially for LTE, because LTE is, has some unique feature, long symbol durations to have a high efficient modulation scheme. We need to solve this problem. And we also solved the demodulation error correction problem, as well as handling cyclic prefix and inter-symbol interference. After overcoming these challenges, we demonstrated that it is possible to backscatter the ubiquitous LTE signal. For the third contribution, we implemented our design by using a customized PCB and a USRP. We also extensively evaluated the system in 3 real-world scenarios, including a residential home, a shopping mall, and an outdoor environment. Moving to the last piece of this presentation, we will answer some frequently asked questions by the reviewers and our readers. The first question: why do you need to avoid the primary synchronization signal, or PSS, and the secondary synchronization signal? The reason we need to avoid PSS and SSS is that they are very important for the demodulation process. They are the key signals to conduct a faster Fourier transform. The LTE receiver needs these signals to synchronize with the sender and obtain the starting point of a fast Fourier transform. This is the first step to demodulate an OFDM signal. So we designed a low power circuit to first detect the PSS signal based on its features, and then avoid modulating or affect the PSS signal passed to the receiver. The second question: does the modulation cause cross-channel interference or inter-symbol interference? Since we need to shift the backscatter signal out of band to avoid the mutual interference with the original LTE signal, the concern is, do we cause cross-channel interference to the new channel? We noticed that different from Wi-Fi, which usually has back-to-back or even overlapped channels, the LTE allocation shows that LTE usually does not have adjacent bands. This is also a reason why we think the LTE signal is a better excitation signal for backscattering. For the inter-symbol interference, because we strictly follow the LTE physical layer when backscattering, the symbol duration and the symbol rate of the backscattered signal is the same, exactly the same as the LTE signal, the original LTE signal. Furthermore, we also dealt with a cyclic prefix to prevent inter-symbol interference. The last question is, when compared with Wi-Fi-based backscatter systems, does airscatter achieve longer communication distance? The short answer is yes. There are several reasons. First, most LTE bands have a frequency lower than 2.4 or 5 gigahertz. We know that lower frequency electromagnetic wave transmits further. Second, the LTE channel is designated, so there is virtually no interference from other devices. Other devices, protocols are not allowed to use the LTE channel. Third, and most importantly, cellular towers have much higher transmission power than Wi-Fi AP. This is very good and important for backscattering. Thanks.
Thanks for the exciting talk, Ziteng. We have questions coming in on Slack, but before, as they come in, I'm just going to ask you one question from my end. And I really like the fact that you focus on this universal availability aspect and the continuous signal transmission of LTE. So one of the things about the system is that you move the backscattered signal to an adjacent frequency band. But in LTE, there is a lot of issues about spectrum access. So how do you envision that you would navigate that? Because the adjacent band might not always be available for LTE, and even if it's available, it might be controlled by a different operator.
Yeah, that's a good question. Also, we saw this question from the reviewer, and this is a concern how to actually commercialize our backscatter system. So we believe one thing is we observed that some of the LTE bands, there's adjacent channel, and if there is one or there is one that belong to the current for example the company, the cellular company, then we may need the company to work together, because this is a commercial channel. So
Hey, Ziteng, I think you're breaking up, so it might be better to turn off the video and just have an audio connection.
Can you hear me now? Hello?
Hey, yeah, so I think you're breaking up. Can you turn off your video maybe and just have an audio connection?
Okay.
That might work better.
Okay, how about now? Can you hear me?
Slightly better, yeah.
Also, okay. So this is one of the concerns about how to commercialize our backscatter. Yeah, this is important band if the adjacent band is not belong to current. And then our answer will be want to then we may need to work together. If the adjacent channel is occupied, is used by different company, then we may need them to work.
Okay, so as I hear from Ziteng, I think I'm getting that the signal is quite bad. So Ziteng, maybe it might make sense to take the Q&A to Slack because there's a lot of questions on Slack around this. So it'll be great if you could answer those. And in the meanwhile, we can move to the next talk. And just to rephrase what Ziteng was saying here for the first question, he's saying that they might need different operators to collaborate together to share their spectrum to make a technique like this feasible.